Okay, this is Dr. Brown. We're going to talk about, in this video, limits at infinity and infinite limits. We're going to see what happens as x goes to infinity and what happens as x goes to other critical values like c and produce values of the functions that are approaching infinity. Okay, first we're going to have some definitions, and to define what we mean by having x go to infinity, we define the expression, the limit of f of x as x approaches infinity equals L, means that f of x has a limit L as x approaches infinity. And so we write in shorthand, limit of f of x as x approaches infinity equal L. And that means that for any small number that you can think of more than 0, you can come up with a corresponding number m that if you make it, that if x is larger than that m, then the value of the function of x minus that limit is less than that small number epsilon. So if you gave me an epsilon equal to like 0.0001, I could find a value m so that if you made x more than that m, that the value of the function minus that limit would be less than 0.0001. In other words, it could get close as you want to the limit that you propose the limit to be. On the other hand, we can say that f of x has a limit of L as x approaches minus infinity, has about the same definition if for every small number epsilon more than 0, there exists a corresponding number n such that if you keep x less than n, that the difference between the function f of x and what you say the limit is will be less than epsilon. Now here's a definition that I know you have seen in college algebra. It has to do with the horizontal asymptote. We say that the line y equal b is a horizontal asymptote of the graph of the function y equal f of x if the limit of f of x as x approaches infinity equals b, or the limit of f of x as x approaches minus infinity equals b. Now I want to go and define what a vertical and an oblique asymptote is. A rational function, and you know that a rational function is basically p of x divided by q of x, where p of x and q of x are polynomials. And a rational function has a vertical asymptote if the denominator q of x has a 0 that is not cancelled by the same 0 in the numerator. So just briefly, if q of x had a factor x minus 1, then x equal 1 is a 0, and x equal 1 would be a vertical asymptote unless p of x had a factor x minus 1 in the numerator so that that would cancel out. So when you're looking for vertical asymptotes, set q of x equal to 0 and solve for x. If you see a factor that leads to q of x equals 0 and it is not canceled by the same factor in p of x, then you have a vertical asymptote. Now there is another kind of asymptote called an oblique asymptote, or sometimes called a slant asymptote, if the numerator has a degree that is exactly 1 greater than the degree of the denominator. And in this particular case, the asymptote would not be horizontal, it would be slanted, and your function f of x would approach, never touch, but get as close as you want it to the slant asymptote. Now, the first function we're going to look at is f of x equal 1 over x. The first thing you notice is that x equals 0 is a vertical asymptote. And so the line x equals 0 is a vertical asymptote, and you can see that as you approach x equals 0 from the left, you can say that the limit of 1 over x as x approaches 0 from the right, that it goes to plus infinity. If you also look from the left and let x approach 0 from the left, you can say that the limit of 1 over x as x approaches 0 from the left is equal to plus infinity. So those are that is your vertical asymptote, and the limit of the function actually heads to infinity, and excuse me, this is minus infinity is the vertical asymptote. Now, the limit of 1 over x as x approaches plus infinity, you can see quite clearly is 0, and the limit of 1 over x as x approaches minus infinity is also equal to 0. So the horizontal asymptotes are y equals 0. And that is just what we have right here. The limit of 1 over x as x approaches infinity is 0, and 1 over x as x approaches minus infinity is equal to 0. Now, you will recall that if you have the sum, the difference, the product, or the quotient of several functions, that the limit of the sum difference product or quotient of several functions happens to be simply the sum difference product or quotient of the individual limits. So you can add, subtract, multiply, and divide these individual limits. So let's look, and this is pretty much intuitive. If you want to find the limit of the function phi plus 1 over x, which is the sum of two functions, you just add up the individual limits. Obviously the limit of 5 as x approaches infinity is going to be 5. The limit of 1 over x as x approaches infinity is 0, so you add those two up and you get 5. Pretty simple. Now, part B here, we have the limit of a constant divided by x squared, which we can write as a constant times 1 over x times 1 over x. And so that is the product of three functions, a constant, a 1 over x, and a 1 over x. And so you multiply out the individual limits and you get a constant times 0 times 0, and the limit, of course, is 0. Now, I want to show you something that is not exactly in the textbook written this way, but I have found it a quick way to determine the limit of a rational function as x approaches infinity. And it's something that you learned in college algebra or pre-calculus. First of all, a polynomial given by a sub n x to the n plus a sub n minus 1 x to the n minus 1 and so forth, it could have many terms, is always dominated by the term with the largest exponent. So if you want to find the limit of a rational function, which is one polynomial divided by another polynomial, simply write down the dominating term, which is the term with the largest exponent, for the numerator and for the denominator, and then find that limit. Now, to illustrate the fact that the largest of in a polynomial, the term with the largest exponent dominates the function, look at these two functions. First of all, we have a fourth order polynomial with several terms, with the largest exponent term being 3x to the fourth, and we have a g of x equal 3x to the fourth. And obviously both of these polynomials are dominated by the same term. They're identical. So as x gets larger and larger, you would expect there to be no difference between the graph of g of x and f of x. And sure enough, if you put this in your calculator and graph the two functions, that as x gets larger and larger, you see that even as x just gets closer to 2 and larger and larger, that these two graphs pretty much overlap each other and are the same. Now let's look at another rational function which is graphed here. The rational function is given here, and to find first of all, it has no vertical asymptote because there's no real number that will make the denominator 0. You can verify that. But to find the horizontal asymptote, we want to take the limit as x approaches infinity of y, and we would take the dominating term 5x squared for the numerator and 3x squared for the denominator. Obviously the x squares cancel and the horizontal asymptote is y equal 5/3. And so we see this red line here, that is the horizontal asymptote. Here's another example. I suggest you verify everything I'm saying here and graph this. Let's first look at the vertical asymptote. We set 2x cubed minus 1 equal to 0, and we get 2x cubed equal 1, x cubed equal 1/2. So x is equal to the cube root of 1/2, which is just a little bit less than 1. So this red line here is a vertical asymptote, x equal cube root of 1/2. Now to find the horizontal asymptote, we take the limit of 11x plus 2 over 2x cubed minus 1 as x approaches infinity. You can see that this is, the numerator is dominated by 11x, the denominator by 2x cubed, and this looks like the limit as x approaches infinity of 11 over 2x squared, which obviously goes to 0. So y equals 0 is the horizontal asymptote. And indeed, the graph confirms that. Now we have the function y equal e to the x. E to the x goes to plus infinity as x gets larger, but we can write that as 1 over e to the minus x and see that the limit of 1 over e to the minus x as x approaches minus infinity minus x is going to be a large positive number, and 1 divided by that is going to go to 0. So the horizontal asymptote is going to be y equals 0. So y equals 0 is a horizontal asymptote. Now the next example is a sum of two functions, the first being the constant 2 and the second one being sine x over x. Here x is going to infinity. The 2 obviously will go to 2, but notice that sine of x, the absolute value, is less than or equal to 1. And so as x goes to infinity in the denominator, sine x over x has to go to 0. So the limit of y as x goes to infinity is equal to 2. So the horizontal asymptote, as you see, is equal to y equal 2. Next we have another rational function. We'll look at the vertical asymptote first. X minus 1 equals 0. So x equal 1 is a vertical asymptote. and you see that here in red. The horizontal asymptote is a limit of 1 over x minus 1 as x approaches infinity. Obviously the 1 is dominated by the 1 in the numerator, and the denominator is dominated by x. That goes to 0. So y equals 0 is a horizontal asymptote. Now, another slightly different problem, looking at this function, finding the vertical asymptote first, x equal minus 2 is a vertical asymptote. X plus 3 is dominated by x. X plus 2 is dominated by x, so this equals 1. So the horizontal asymptote is y equal 1. And indeed you can confirm that by putting this in your calculator. Next example, the first thing you should do when you see the denominator is try to factor it to see if it's got zeros that you can calculate, and obviously you get x minus 2, x plus 2. So the vertical asymptotes are x equal 2, x equal minus 2, are vertical asymptotes. And the limit of minus 8 over x squared minus 4 as x goes to infinity. The numerator is dominated by minus 8, and the denominator dominated by x squared. This goes to 0 as x goes to infinity. So y equals 0 would be the horizontal asymptote. Now we have another function that has a vertical asymptote. First of all, y equal x is drawn here, which, as you know, has a horizontal asymptote of y equal 1. The inverse function of e to the x is ln of x. So ln of x is the inverse function of e to the x. Notice that you cannot take the logarithm of 0 as x gets closer and closer to 0 from the right. The function goes towards minus infinity. You can confirm this by graphing it. So x equals 0 is a vertical asymptote of ln of x. Now, you all will recall from pre-calculus that you graphed functions like tangent, cotangent, secant, and cosecant, and found you had multiple, in fact, infinite numbers of vertical asymptotes that repeated. To find the vertical asymptote of secant of x, you can write that as 1 over cosine of x, and cosine of x equals 0 for odd multiples of pi over 2. So as you can see, you can put this in your calculator and see that you have vertical asymptotes at odd multiples of pi over 2. By the same token, writing tangent of x as sine of x over cosine of x, the vertical asymptotes again occurs where cosine of x equals 0, and so again you have a different graph, but the same vertical asymptotes at odd multiples of pi over 2. Now, finally, we're going to look at a function that has an oblique asymptote, or sometimes called a slant asymptote. First of all, this particular function has a vertical asymptote where 2x minus 4 equals 0, and so we get x equal 2 would be the vertical asymptote. To find the horizontal asymptote, you need to do a long division, and so you divide 2x minus 4 into x squared minus 3, and as you probably already know, you need to put a placeholder for the terms that aren't there, like the x term, so you have 0x minus 3, and now you do the long division, divide 2x into x squared, and you get 1/2 x, multiply 1/2 x times both terms, and you get x squared minus 2x. Now subtract, and you get, for the first term, x squared minus x squared is 0, and then 0x minus 2x equal 2x. And then you bring down your minus 3, 2x goes into 2x one time. We're almost finished. Multiplying the 1 times the 2x minus 4 gives us this. Subtracting, and we get a remainder of 1. So the slant asymptote is y equal 1/2 x plus 1. And the remainder divided by the denominator, which is 2x minus 4, as you can see, goes to 0 as x goes to infinity. So as x goes to infinity, the blue curve gets closer and closer to the red asymptote. So this concludes our video of limits at infinity and infinite limits.